Hey, so this is Joe, and this is the first video of Chapter 10 in Stewart'c Calculus. And so we're going to be talking about parametric equations and using calculus with them. So in the first section of this chapter, the book kind of goes over how to plot parametric equations, how to parametrize an equation, and how to kind of convert between Cartesian and single parameter parametric form. And I'm not going to be going over that right now. If you need a refresher, definitely look in your book or look at one of our videos in our pre-calculus section. Otherwise, we're going to be starting right off with applying calculus to parametric equations. So first, I'm just going to, there are a bunch of formulas that are given in this chapter for parametric equations, but these are really the three that you're going to need to know on the AP. The surface area and all that, that's not really going to show up on the AP. These are what you need to know. And I'm going to go over them in more depth, kind of explaining them, even though there is the nice, fully fleshed out proofs in your book. So first, we've got how to find a tangent. So a tangent is dy dx in Cartesian form, and when we parametrize the equation, we get dy dt over dx dt. And you see that these dt's will eventually cancel out, and you'll get this. And this comes from the chain rule. I'm actually just going to explain this right here because it's a super simple concept. So we have dy dt is going to be equal to dy dx times dx dt, and you see and so that's the chain rule, right? And if we divide dx dt over, we'll get this equals dy dx. So that's how we find a tangent. And so now for the area under a curve, I'm going to actually have to go over to another screen and explain this, but the area under a parametric curve is going to be between alpha and beta, the y function in terms of t times the derivative of the x function in terms of t times dt, and I'm going to explain that later. And then arc length, I'm not going to go through the numerical proof here. It's in your book and it's really well described, and you don't really need to know the numerical proof, but it's a very easy formula to remember and kind of get. So the length is the integral between a and b of the square root of the square of dx dt plus the square of dy dt. That's all you need to know. You don't really need to understand where this one comes from, but I encourage you to do so because it's interesting, and that's kind of what maths is all about. So look at that proof in your book. But the area under the curve formula, I'm going to kind of flesh that out in the next slide. I'm not going to give you the full numerical proof, but I'm going to kind of show you why it works. Okay, so ultimately we're going to be thinking about this proof as kind of a U substitution, and you'll see what I mean by that later. But so we're going to start off with the function y equals f of x, and we want to find the area under it, and of course that's in Cartesian form. So the area is going to be the integral between a and b of y dx, so f of x dx, right? We know that one. But let's say we parametrize this, and we get y is equal to some g of t, and x is equal to some h of t, such that that's the parameter of y equals f of x. So how do we go about converting this? Well, let's think about it as a U substitution, where the t is the u, the t is the parameter. Well, what we need is so we have the y, we can substitute a g of t in for the y, but we need to take care of this dx, and this dx is differential we can get by taking the derivative of x with respect to t. So we want dx is going to be equal to h prime of t times dt. Now we have our y, we have our dx, we just substitute in for that. And this a and b, those are going to change, those limits are going to change based on the parameter, so we'll just call that an alpha and a beta. For the y, we put in a g of t, and for the dx, we get an h prime of t dt. So we can really think of this as alpha and beta. So the g of t is really y in terms of t, and so we can kind of write that in a rugged way out as y of t. And the h prime of t is really just the derivative of the parametrized version of x, so we could always just write that in crudely as x of t, so we remember which part of the function that is, and then dt, and that's the area under a parametrized curve. And so that's kind of all you need in terms of explanation for how to do sort of apply calculus to parametric curves. And applying these formulas isn't very difficult. Sometimes conceptually using the formulas based on the questions are difficult. And so I'm going to go over kind of one of the hardest sorts of questions you're going to need to use these concepts with, in addition to a pretty easy just tangent problem. And we're going to do that tangent problem first. Alright, so number 19 on page 675 in your book asks, when is the parametric curve horizontal and vertical? Or vertical, sorry. And so we've got the parametric equation, x equals cosine theta, y equals cosine 3 theta, and the theta, you can think of that as just the t, that's a parameter. And so because these are both trig functions, we have the implied rule that we're just going to be looking at theta between 0 and 2 pi. So we know that with a Cartesian curve, it's going to be horizontal when dy dx is 0, so that's horizontal, and it's going to be vertical when its dy dx is undefined. So we have our formula, our tangent formula for, and remember this is tangent to the curve, horizontal or vertical. So we've got our formula, dy dx for the parametric equation is going to be dy, in this case, d theta over dx d theta. So what we have is when dy d theta is 0, it's going to be horizontal, right? Because that's going to make this entire expression 0. And when dx d theta is 0, that's going to be undefined, because we'd get a 0 in the denominator. So this makes solving these kind of expressions pretty easy. You don't need to like combine these into a fraction and then figure out when it's when the tangent's going to be horizontal or vertical. You can just take the derivative of each part of the equation, and based on which one it is and when it's 0, figure out when the tangent to the curve is horizontal or vertical. So first off, we're going to figure out where it's going to be horizontal. So we're just going to be dealing with the derivative of the y component, dy d theta. So we've got dy d theta is going to be equal to the derivative of cosine 3 theta with respect to theta. So what's the derivative of cosine? Well, it's negative sine, but we're going to have to bring a 3 out, so it's negative 3 sine 3 theta, and then we ask ourselves, when's that 0? Well, it's going to be 0 when sine 3 theta is 0, and that's 0 when 3 theta, the argument, is 0 pi or 2 pi, so that means it's going to be 0 when theta is 0 pi over 3 or 2 pi over 3. So now we have to do the same, and so that this is going to be when the tangent is horizontal. Now we have to do the same thing for dx d theta to figure out when the tangent is going to be vertical, or when the derivative is going to be undefined, when dy dx is going to be undefined. So we have to ask ourselves, so what's the derivative of cosine theta? It's negative sine theta. And now this is easy. When's negative sine theta 0? Well, it's going to be 0 when theta is 0 or pi or 2 pi. So these are the moments when the tangent is vertical. And that's that problem. That's all you need to do to solve this problem. Pretty straightforward, just some kind of straightforward trigonometry and differentiation. Now we're going to move on to something a little bit more difficult. So now we've got number 31 on page 675, and the question asks us to find the area enclosed by the ellipse described by the parametric equation x equals a times cosine theta and y equals b times sine theta. So this is basically the general equation for any ellipse, because the size of the ellipse along its major and minor axes just depend on the b and the a, but the shape or the kind of function as an ellipse is going to always remain constant based on this equation. So what we need to do to find out what the area is start kind of getting, either you can graph it or get a sense of what the function is going to be doing. So we're just going to kind of draw out a general ellipse. It looks really ugly here, but it's an ellipse. So when we have theta, and remember theta is always with respect to the x-axis in the first quadrant, when we've got theta is equal to 0, Well, our y is going to be 0 because sine of 0 is 0, and the cosine here, cosine of 0 is going to be 1, so x is going to be a. And then we can imagine if theta was pi, y would continue to be 0, and this point right here would be negative a. And when theta is equal to pi over 2, this sine is going to be 1, so the y is going to be a b, and the x is going to be 0 because cosine of pi over 2 is 0. So this is a b, and then down here you can imagine is a negative b, 3 pi over 2. So we've got a, yes, so these are the points we have at certain point values of theta. So this is when theta is 0, this is when theta is pi over 2, this is when theta is pi, and this is when theta is 3 pi over 2. So what we want to find is we want to find the area in here inside the ellipse. Well, what we could do is we could try to integrate for the whole function, but that gets a little messy because we dip under the x-axis, and you can do it. But what's easier to do is say, well, look, all ellipses have symmetry. The area under there is going to be equal to the area under here. So why not just find this area? Oh, and remember, this is a parametric equation, and it parametrizes this way because of the way these trig functions are set up. I mean, they operate like trig functions as it goes. It goes counterclockwise. So we can find this area between theta is 0 and theta is pi, and then just multiply it by 2, right? Yeah, we can totally do that. So what we have to get out here first is our little area formula. So area alpha and beta, well, alpha is going to be 0 because 0 comes first in the parametrization, right? You put a 0 here and into theta, and the x's and the y's start moving this way until you get theta equals pi, and you get over here to negative a. But so we're going to go between 0 and pi, and the y is b sine theta, so we're going to get y in terms of theta times the derivative of x in terms of theta d theta, and that is going to be our expression for the area. Now let's go into the next page and actually solve that. On that previous screen, the A was only half of the area, total area enclosed by the ellipse, right? Because that was just between 0 and pi. Now we've got our total area, and it's going to be 2 times that half area, because remember the half area is just between 0 and pi. So let's start plugging in values, but first let's find the derivative of x with respect to theta. So we're going to get our x prime in terms of theta is going to be, what's the derivative of cosine? It's a negative sine. So we're going to get negative a sine theta. We've already got our d theta out there. So we're going to get 2, 0 and pi, negative a b sine theta, and then this sine theta makes that a sine squared theta d theta. So it looks, so we've come, this is a little bit tricky. How do we integrate sine squared theta? There's no u substitution we can make. If we make it 1 minus cosine squared theta, there's still no u substitution we can make. And we can't break that up into a fraction and use a natural logarithm. And this is already a trig function. We can't do another trig substitution. So how do we go about this? Well, we're going to have to fall back on the properties of trig, like the trig properties that you learned in pre-calculus that you might forget, that you might have forgotten. So I'm going to give you a refresher on one really important one that you're going to want to use when you're doing integrals like this, and that is that sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. It's a really random property, but it makes solving integrals like this a lot easier, and it makes them possible. So we're going to make that, we're going to take the negative 2ab outside of the integral as a coefficient, and then we've got 1/2 minus 1/2 cosine 2 theta d theta, and now we can integrate all this. This is all pretty easy, and we can even split it up into 2 integrals if you'd like. So now we've got 2ab times, and then we integrate 1/2 with respect to d theta. That's just going to be a 1/2 theta between 0 and pi, and then this minus half we can take out, and then the minus and a minus becomes a plus, and the 2 goes away, and we're going to get an AB, the integral between 0 and pi of cosine 2 theta d theta. And so let's go into the next screen to solve this. Alright, now we can start solving. You put a pi in there, that's going to be 1/2 pi, but a 0, that's going to be a 0. In any case, the 2's are going to cancel, so you're going to get a negative pi AB, and the rest is 0, plus AB, and now what is the derivative of what is cosine? The derivative of sine is cosine, so the derivative of sine 2 theta is going to be cosine 2 theta, but remember we need a coefficient out here to take care of the 2, and so that coefficient is going to need to be a 1/2 sine 2 theta, and that is going to be evaluated between 0 and pi. So now we can come down further. We're going to get a negative pi AB plus 1/2 AB sine 2 pi, because we plug in for the pi, minus 1/2 AB sine of 0. And so we're going to bring down this negative pi AB plus, and then sine of 2 pi, that is 0, minus, and then sine of 0 is also 0. So we come out with that area being negative pi AB. But this is weird, an enclosed area being negative. So already we know that we didn't do something wrong, but we did something odd that we didn't foresee with the parametrization, because you can't have a negative area. When we talk about negative area, that's only conceptually and graphically. Really what we would be talking about is like a negative distance, negative displacement, negative number of bacteria or something like that. But so this negative can't really be there, but that doesn't mean this answer is wrong. This answer is probably right. What it probably means is we just integrated the wrong way. We should have integrated underneath, and that would have been our positive area, because you've got a parametric equation that can come out of it. So what we really should have been doing is this should have been a negative pi. And so that would have meant that we would be integrating clockwise, and then the half that we integrated was the half underneath the x-axis. So instead, we're taking the area of this between 0 and negative pi, but remember negative pi is actually pi, it just is a directional thing. So if we just replace all of these with negative pi's, negative pi there included, that becomes a plus, that becomes a plus, that becomes a plus, that becomes a plus. Those are still all zeros, so the sign doesn't matter. And then we'll get positive pi AB, and that is the total enclosed area. So that's it for this video. Stay tuned for the next one. We're going to be doing polar coordinates and polar equations with calculus, so stay tuned for that. Thanks.